Great. My name is Chirag Patel. I'm here to introduce you to the next session here. It's a very timely one given the amount of new data modalities and infrastructural advancements we've had in the recent decade or so. It's officially the session 3, the Exploring Novel Research Tools to Advance Decision Making and Enhance Causal Inference here. So. On behalf of the committee, I'm your moderator, along with Margaret Carragus as well, to take you through here. So our first speaker of this session is Dr. Vincent Cogliano, and we'll be hearing about 20th century causality frameworks are evolving to fit 21st century data. So, thank you.
Well, thank you very much for that introduction. Thank you to the organizers for inviting me to speak at this session. Let's see, do I have to start this? Okay, well I'm going to... Okay, thank you very much. So I'm with the U.S. Environmental Protection Agency, and I'm going to be talking about a few topics. First, I'm going to do a historical overview of how we've used experimental data in our hazard assessments to infer causality about various agents in the environment. Then I'm going to talk a little bit about the key characteristics, and I actually have some numbers on the question that came up earlier about TOX21 assays that are associated with each of the key characteristics. And then I'm going to talk about some of the challenges that were identified in the NAS recent report on TOX21 data. So in the early days of risk assessment or hazard assessment, I'm really talking from about the 1970s really through about the mid-1990s. I would call that the pre-mechanism age. And we were looking only at apical endpoints only. Does this cause cancer in animals? Does it cause reproductive decreases? Does it cause neurotoxicity in animals? And it was tested in various strains of rats and mice, depending on the outcome you were looking at. And what we were looking at was replication. And if something was replicated in multiple test systems, you had more of a confidence that it would be relevant to humans. And the cancer guidelines at EPA, the guidelines in the IARC preamble, pretty much these are quotes from those. 2 or more species, independent studies at different times, different laboratories, different protocols, more than one sex species strain, exposure route. This was the type of replication we would look at, and the more something was replicated in different systems, the more confidence we had that it would apply to humans and it would be used as in causal inference. In the mid-1990s, I'm going to call it the early mechanism age, this paradigm of replication of apical endpoints in different systems started to not be very satisfactory, because what we had was most of the data that was being done was on various mechanistic... Oh, where's that going? I thought it was a little mouse running across my... something dark. Anyway, most of the research that was being done in universities and laboratories across the world was not these 2-year bioassays, but really does something cause genotoxicity? Does it cause oxidative stress? How does it affect cell growth? And how do you put all that together? And the way we would put that together would be through, initially proposed as mechanistic pathways, where you looked at an animal exposure, the dose to a target tissue, you used toxicokinetics to get the dose to the target tissue. You'd look for cellular responses, then you get various key events that would be building up to an apical endpoint in the animals. And you would try to get that kind of an understanding. Dr. Smith had a very good comment this morning, or earlier this afternoon, about that you don't want to look at just one pathway. You can have multiple pathways, and this is somewhat suggestive of one pathway, and that one pathway is relevant or not, it's well established or not, and there could be multiple pathways. But this is how we got started in the early mechanism age. There were multiple uses of mechanistic data. One is to augment the human or animal evidence, and in Paul and Vineas's talk, he talked about this meet in the middle. If you do have a sequence of events that lead to your apical endpoint, you could start to get very good evidence that the chemical causes this intermediate event, and other studies might say these intermediate events are associated with apical endpoint, and that gives you additional confidence if maybe your epidemiology studies of just linking the apical endpoint with the chemical exposure are confounded by too many variables or not enough to make a confident inference. You could start looking at these intermediate steps and build your confidence or evaluate whether your confidence is justified. Another is to identify susceptible populations. That's if you have multiple events that are involved in causing the apical endpoint, you can start to say, well, what population or life stage might be more susceptible to this event happening or have it happen at a higher rate? And that gives you clues to susceptibility that complements what you might see in an epidemiology study where you have sub-cohorts, you do some subgroup analyses and you say, this subgroup is responding more than that subgroup. It's the observation of the apical endpoint. Mechanisms gives you a complementary source of information to say, we think this event is associated with this outcome, and here's a population that is likely to be more susceptible to that apical endpoint. Most of what was used, this kind of mechanistic data and pathway is to evaluate human relevance. And there what we would do is try to elucidate one mode of action in animals, evaluate the concordance of the different key events or the toxicokinetics across species, and then argue about and eventually decide about whether to discount positive results in animals. And so in the mid-90s, IARC changed its preamble. EPA started changing its cancer guidelines to say that you could have positive results in animals that could be discounted if you had strong evidence that these mechanisms were not operating in humans. And so that's really where it started. Mechanistic data also could be used to supplement, for example, a human data set that didn't have sufficient evidence in humans, but you had strong evidence in animals, you had some understanding of the mode of action in animals, and you had some understanding that the mode of action in animals was applied to humans. When I was at IARC, I would say we probably had more than a dozen and a half agents that were upgraded because of this kind of mechanistic understanding. And at EPA, just in the last 3 months, we posted benzoate-pyrene and ethylene oxide, neither of which had compelling human evidence, but we had the whole story with the mechanistic evidence, and call those human carcinogens. Where we're going right now is pathway-based, and I will accept Martin's correction that this really should be network-based, basically networks of pathways, and we have multiple ways to get to an apical endpoint. But basically, we're going to, the focus instead of is on, not on apical endpoints, but on pathways and linkages. And we're identifying key events and pathways that might, multiple pathways that might lead to an apical health endpoint in humans. And then we test whether the agent can perturb those pathways. Now, one of the things I think that is in the back of people's minds too is we're not trying to use these pathways and networks to replicate animal bioassays. We're really trying to get the events that are going to be expected to be observed in humans, and this will be done in human data. This also gives us the opportunity to say that the effects might be induced by either the agent we're studying or other factors. So something does not need to be a complete carcinogen, but it could affect one or more key steps in the carcinogenesis process, and in that case, increase the incidence of human cancer, even though it doesn't do everything along a pathway. And we are getting large volumes of data on various intermediate steps, markers, processes, but not less and less, as Martin's talk started with, less and less on apical endpoints. So I want to talk a little bit about the experience at IARC. So we did look at all the more than 100 human carcinogens, and rather than just confirming that they all caused human cancer, what we wanted to do was do something that was filled some gaps in risk assessment. So while we were evaluating all of these carcinogens, we also said, what are the tumor sites? So for example, with tobacco and smoking, that one of the first Surgeon General's report caused lung cancer in men. Well, now we have about 12.5 cancer sites that are associated with smoking. And that's been the case with a lot of carcinogens. We found more and more tumor sites, and that's really sometimes very important to public health. It's also important to designing good epidemiology studies because you want to know what confounding factors you need to look at. And this information, I think, has been very helpful in designing epidemiology studies and knowing what kinds of confounders should be considered in the design or the analysis. We also have the mechanistic aspect of identifying established and likely mechanistic events with the idea of coming back later and seeing what that all meant. Most of the human carcinogens were evaluated the previous time. This evaluations were done in 2009, 2010. Most of the group 1 carcinogens were first identified before the mid to late 1980s, before there really was much mechanistic research. So this gave us the opportunity to collect that mechanistic database and to decide what was happening. So we developed this over the course of 6 meetings in 2 years involving 160 scientists. And we came up with 6 volumes of IARC monographs, but also later on, as Martin had said, we had a series of 2 workshops where we looked at the mechanistic data, and we eventually came up with the 10 key characteristics of carcinogens. And this is a slide, I think, that Martin had, or this is put into one slide with smaller typeface and a smaller font and maybe fewer words. But basically, each of these key characteristics has a lot of different assays that would feed into it. So it's not just 10 assays, it's dozens or hundreds of assays that all feed into these key characteristics. And here's a slide that Ivan Ruzin, a couple of years ago, tried to map the TOX21 assays into the key characteristics. And I think, just like Martin said, we really had the receptor-mediated effects are very heavily represented there. And next is the cell proliferation and cell death types of assays. But there are some, like the Judovic instability, which is really very important up front. Immune suppression, immortalization that aren't covered by any of the key characteristics. And some of the others are not really, there's not a lot of TOX21, TOXCAST assays. So this points to where we might want to develop assays for these characteristics. Now, data overload. When I was at IARC, when I'm at EPA, well more than half the studies, probably 80% of the studies, really all do fall into the realm of mechanistic data rather than apical endpoints in epidemiology studies or animal bioassays. And the point is to not get totally swamped with all of these data. So what we do is we take our mechanistic studies and we sort them out, and there's into the different bins of key characteristics. And then we analyze them, but we analyze them judiciously. So here's our process of doing an assessment. We have scoping, problem formulation, protocols, then 5 steps that the Academy identified for in IRIS assessments. And then in the later report evaluating IRIS, they had arrows going for human and animal and mechanistic data streams. Now, I made the mechanistic data stream much wider because there's a lot of studies there. And that could really get us bogged down. So what we're using the key characteristics to do is to take that mechanistic data stream and defer the analysis of that until we know what we really want to do. So we take the human and animal data, we put it through a preliminary integration, and we then go to another problem formulation of mechanistic studies to find out what are the questions we need the mechanistic data to answer. Then we take that huge stream of mechanistic data and identify the pertinent subset of those data that we need to analyze, look at the studies, do the analysis, and then have that feed up into the overall integration. It's still important to be systematic. If you're going to try to measure a rate, you're trying to measure a dose where you're going to get oxidative stress in humans, you want to make sure you're looking at all the studies and not just a subset of those studies, so you really can answer that question. But we will try to do things like reconcile different results. Why does something show up in one strain of animal and not another? Who's susceptible? What approaches should we use to dose response assessment? what are the precursor events to the apical endpoint that maybe we could use for developing a reference dose? So these are the types of mechanistic questions we would put into that problem formulation. Now I want to talk about the implementing the TOX21 vision. And basically, there were 5 recommendations in the recent National Academy's report. Developing case studies that test approaches, better understand the linkages, incorporate new data, better understand uncertainties, and promote discussion among scientists and various stakeholders. So I'm going to talk a little bit about each of those. The case studies, it's really going to be difficult to try to write any kind of guideline right now about how you would use these new studies. In fact, even with mechanistic studies that we've had for 20 years, the IARC preamble or EPA's cancer guidelines basically says you can develop sufficient, limited, inadequate evidence in humans or animals by looking at whether you have chance bias and confounding ruled out with reasonable confidence, things like that. But for mechanistic data, we simply said, characterize it as strong, moderate, or weak without any kind of real guidelines, because new studies are coming out all the time, new mechanistic insights are coming out all the time. We're not able to do that. And I think we're going to be in that realm for quite a while. So the idea is to be flexible and open to be able to use your judgment and decide when we do have sufficient understanding to be able to characterize and maybe even classify a hazard based on mechanistic data. The IARC preamble in 2006 was modified to say that you could call something a possible carcinogen based on mechanistic data alone without human or animal studies of cancer when you had sufficient understanding. How much is enough? Well, that's going to involve a lot of discussion across scientific disciplines and with diverse stakeholders. And to get the diverse stakeholders, these data are going to be a lot harder to understand than an epidemiology study where you have people getting sick. Everybody can understand how, when you describe the results of those studies, or even that animals, rats and mice, are getting sick. But to say that you're changing gene expression, you're changing some immune markers, that's going to be harder for people to understand the true importance of that. Understanding disease pathways, we certainly have a lot more to do there, and that's going to be important. Developing key characteristics of other disease outcomes is something I think we would like to do at EPA, and I think that the value we've already been seeing in cancer can be used elsewhere as well. Again, retaining flexibility to accommodate new assays that are being developed and new understanding. And I also have a slide from the Goodson paper that this pathway-based understanding really helps you incorporate non-chemical, not other factors that might be contributing to your disease risk. And so instead of looking for complete carcinogens, which is what most cancer bioassays, for example, would test, or what most assays of any chemical and the disease endpoint cause, we can start to think about some of these intermediate steps that might be handled by other exposures. Evidence integration, 2 parts to this. One is integrating the new data into syntheses of conventional toxicology and epidemiology. So right now we kind of know how to put together human and animal data, and we want to, as number of bioassays and the number of epi studies of apical endpoints are decreasing, we want to be able to take the mechanistic data and say, yeah, this can substitute for those data, or this can contribute to our confidence in the data that we do have and lead us to a conclusion that we do have a hazard. And eventually use new data for causal relationship. The slide that we have, epidemiology studies on tens to hundreds of agents per year, bioassays on a similar number of agents per year, but we're developing thousands of new chemicals per year. We're going to have to be able to use these kinds of studies to make causal inferences to keep up. Again, emphasis on transparency, communication, and talking with stakeholders. There's also the difference between being protective and being predictive. We like to think of our pathways and networks as being predictive, but health agencies have also the responsibility of being protective. and not sort of betting the public health on something, even though it seems like it's a good bet. We have to really make sure that we are protective and protective of multiple pathways, multiple subpopulations, and so on. So uncertainty, we have to generalize our data sets across metabolic pathways, different exposure scenarios, life stages, sensitive populations, and other aspects, and communicate these. And when we have our pathway-based conclusions disagree with a bioassay, we have to be able to have confidence to be able to explain that discrepancy. So in conclusion, or in summary, basically these new approaches are going to bring very profound changes to risk assessment. The key characteristics, I think, are giving us ways of addressing this in the cancer realm. We need to extend this to other realms. There are a lot of challenges, but there's a lot of things that we can do with a lot of smart people to realize this vision. So thank you very much again for your attention.